4.0 is not included?
Right. So yeah, it just goes up through chapter 3.
Okay, cool. Just making sure.
Yep.
And then we're also going to have a review session tomorrow during class, right? Basically.
Correct. Yeah.
Okay, cool.
All right, let's go ahead and get started. So, Sebastian, I think you were first.
Okay. So I just have a quick question. It's with chapter 3.7 with L'Hopital's rule.
Yeah.
The question is number 7 on like the review or whatever, but it's basically the limit as theta equals pi.
Hold on, let me share my screen here.
Okay.
All right, so the limit as
You could say x equals pi over 2. And then the question is 1 minus sine x. And then 1 over 1 plus cosine 2x. Yeah.
like that? Okay.
Mm-hmm.
Okay. And what question is this? This is from the book. So section 3.7, what question is this?
This is question 7.
Okay. All right.
So starting out just by looking at it, we can tell that it's differentiable or whatever. Yeah, that's what it is. Because it goes to infinity over infinity. That's the that's what it go to. Or is that the right word?
I mean, it goes to 0 over 0, but
oh yeah, sorry, because it's sine and cosine.
Yeah, you can still do that. Right, so that's true. So then from there, what can we do?
So then you want to get the derivative of the entire thing. So the derivative of that would be negative cosine over negative 2 sine 2x.
Okay.
Yeah, and it just becomes positive. And then from there, I plugged in pi over 2.
Mm-hmm.
And I got negative 1 over 2 times 0, which is incorrect because that's not what the answer is.
So you got negative 1 over 0, essentially?
Yeah.
Okay. So this goes to this thing, right?
Yeah, basically. That's what
You
I
said
got.
negative 1, I guess? Oh,
yeah,
no.
negative 1.
Wait, cosine of pi over 2 should be 0.
Wait. Oh, okay, yes. Yeah, sorry, it is 0.
Okay. Oh, wait, but I think this is easier than we thought here. So cosine of pi over 2 is 0.
Mm-hmm.
What's the sine of sine of pi? Never mind. So this is still 0 over 0, right?
So like that's my question as well. So like at the bottom part right there, the 2 sine 2x, when you're plugging in pi over 2, do you multiply that 2 with pi over 2?
This one, yeah.
Is that how you? Okay. So then that would technically be 2 pi over 2, which is just pi. And so, oh yeah, that would still be 0. So it said that the answer for number 7 is 1 over 4. Hold on, let me double check that.
Yeah, I agree. I think that's gonna be right.
Yeah, it says it's 1 over 4. So I'm confused at like how they got that answer.
So we got an indeterminate form again, right?
Yeah.
So we still can't find the limit unless we do what?
Unless we get the derivative again.
Yeah. So I mean,
okay.
Yeah, there's nothing saying we can't do this more than once. So this derivative would be negative sine of x over 4 cosine of 4x. No, not 4x. What am I doing? Okay. Now, what happens here?
Basically the same thing. We plug in pi over 2. And so the top would be -1 and the bottom would be -4. Okay, so then it's positive 1/4. Okay.
Yep.
I see.
Mm-hmm.
Okay. So basically what I did wrong was that I just needed to get the derivative again, right?
Yeah, well, it sounds like after you took your derivatives the first time, I think what you said to me was that you thought it was 1/0, which, if you believe that, then you can't do L'Hopital's rule again.
Yeah.
So yeah, you mean you did need to take a derivative again, but since you evaluated these trig ratios incorrectly, I think that told you that you could not use it again.
Okay. And then kind of similarly, I have another question like that as well.
Let's go around and we'll come back to you.
Okay.
Jonathan, I think you were next.
Okay, yeah, I have a question about 3.3, which is talking about inverse functions.
Okay.
I was looking at problem, what was it? 52 on page 170. So if you, it's y equals e to the negative x cosine 2 and then x. And then
Cosine of 2.
Huh?
Like this?
Oh no, it's cosine to the 2. Sorry.
Oh, cosine squared. Okay.
It's cosine squared. And yeah, all that is over x squared plus x plus 1.
Okay. What are we trying to do with this?
We're trying to, we're using logarithmic differentiation.
Okay. I didn't know we needed to do.
Yeah, or we can use an alternate method to find the derivative of a function.
Okay, so yeah, so it's giving you a choice. What do you want to do? You want to do the log method, or do you want to do
can we do it the log method? I'm not that strong on that,
so and to be clear, I think this is probably almost certainly the more effective way to go. You can set up so doing this without using log differentiation. If you want to do it directly, you would have to do the quotient rule, but then nested inside that quotient rule, you'd have the product rule also happening, and there's just a lot of ways to get tripped. So in log differentiation, I want to take the derivative of I want to take the natural log of both sides. So once I've done this, what am I allowed to do?
separate them. You get natural log of e to the negative x cosine squared x minus natural log x squared plus x plus 1, right?
Yeah, minus the natural log of x squared plus x plus 1. Can I do any more than that?
And then you can take the derivative of the inside and the outside, right?
I think there's something we can do before doing the derivative. I think I want to still keep breaking this down.
Then you could separate it by saying natural log of e to the negative x plus natural log of cosine squared x, and then that'd be the same for the other side as well. Or
yeah, this one, and I'm glad you caught that. This one, this x squared plus x plus 1, we're stuck with that. That can't be simplified any further.
Okay.
Now, I think I still want to do some more algebra before I try the derivative.
Well, I mean, are you talking about maybe messing with x squared plus x plus 1? Because
You can't really do anything with that.
would that, and then it'd have to be the cosine squared, right?
I mean, I think I can do something with the, so let's just take a note of what we've done. So this right here comes from, actually this one we use the quotient law
Right.
of logs. This one right here, we use the product law. And this one right here, we are going to use the exponent. Because the derivative of the natural log of cosine squared of x is way nastier than the thing I can substitute for it. So this one I'm going to do, I'm going to bring down the negative x times the natural log of e.
Okay.
This one I'm going to call this 2 times the natural log of cosine x.
Okay.
And that.
Gotcha.
So I think from there, that's probably as simple as I can go. Actually, there's one more thing here. What is the natural log of e?
It's 1.
It's 1. So I'm going to do that as well.
Negative x. Okay.
Yep. So now I think I'm ready to take a derivative. So what is that derivative going to look like?
Negative 1 plus 2 over sine x minus.
So it's actually not going to be 2 over sine. So let's think about how chain rule is going to affect this here. So let's off to the side here. What is the derivative of the natural log of x?
1 over x.
1 over x, right?
Yeah.
So basically we have the natural log of cosine of x. So we're going to have to involve the chain rule. So this will be 2 times 1 over not x, but cosine of x.
And then all that times the sine of x?
Not sine, or almost negative sine of x.
Yeah, negative sine of x. Sorry.
Yep. And then a similar thing here, minus.
Yeah. So then
Go
you
ahead, Jonathan.
do 1 over x squared plus x plus 1, and then you get times 2x plus 1.
Yeah.
Okay.
All right. And something we didn't do, we got to differentiate the left-hand side too. So what do I get when I take the derivative of the natural log of y?
It's just 1 over y?
Not just 1 over y. 1 over y times dy dx.
Okay.
So this right here is what allows us to find this derivative.
Okay.
So from here, do I have enough room to finish this off? I get dy dx. Basically, I'm going to multiply both sides by y. And that's going to give me this. Negative 1 minus 2 times tangent of x minus 2x plus 1 over x squared plus x plus 1. And then I have to multiply this whole thing by y. And what was y? It was e to the negative x cosine squared of x over x squared plus x plus 1.
Okay.
So, I mean, these derivatives that come out of this process, I think they always look really complicated, but I don't think the process to getting them is as, I mean, like I said, you can do the quotient rule. In fact, something I might encourage is, at least start the quotient rule and see what it looks like.
Gotcha.
And I think you'll realize that there are a lot fewer traps doing this.
Yeah. Okay. Well, thank you. I appreciate it.
Yeah, of course. All right, Hugh, what do you got?
Yeah, one sec.
Okay.
So it was a maximum minimum problem. They wanted us to find the absolute minimum and the absolute maximum, and basically like what their X values were that gave us that.
Okay, so just to be clear, this chapter 4 stuff is not going to be on the test. I'm totally willing to answer this question, but wanted to make sure you knew that the test is not going to cover this stuff on Wednesday. You still want to look at it?
Hello?
Yeah, if you were talking, you were muted. So
Okay. I mean, yeah, I can give you the problem real quick and we can do it.
yeah, let's do it.
All right. It's f of x equals negative x over the quantity 7x squared plus 1. And the it was 0, or I guess like the bounds were from 0 to 2.
Okay. Cool. And what are we looking for?
They wanted us to find the absolute minimum and the absolute maximum, and like what values of x attain those numbers.
Okay. All right, I want to find absolute extrema. So what do I got to do to look?
Well, the first thing I did is I tried to find the derivative so I could know where the slope was also 0 on the graph.
What's the derivative of this thing?
I think, let me see. I got, where did I put it? One second.
Okay.
Looking through my work. Where did I get? Okay, yeah. So I think I got 7x squared minus 1 over 7x squared plus 1 quantity squared.
7x squared minus 1
Yeah,
over 7x squared plus 1 all squared.
yeah.
Let me check. So negative 1 times this. Minus negative x times 14x. All right, I agree.
All right.
Okay, so.
And then I wanted to find where the denominator was equal to 0.
Okay, so if you set the denominator equal to 0.
And that's where I had trouble with this problem.
Okay. 7x squared plus 1 equals 0. I mean, really, I just square root of both sides first, but from here, I don't think the denominator is ever going to be equal to 0.
Yeah. And that's kind of where I got found some trouble with this problem.
Okay. So what you have found is that, f prime of x is defined everywhere on this interval, right? Because we failed to find places where it would be undefined, right?
Yeah.
Okay. But you can find there might still be critical points or critical numbers.
Well, wait a second. Isn't it undefined for the square root of a negative number?
We're not taking square roots though.
Okay, but weren't we trying to solve for x though, so we knew which x value had 0 slope?
Yeah, that's why I'm saying that this derivative is never undefined. Because for the denominator to equal 0, I would need x to be the square root of negative 1/7, right?
Yeah. Okay. I see what you're saying. Yeah.
So that can't happen. So
I have a quick question, actually.
Yeah, go ahead, Sebastian.
So why is it that we use 7x squared plus 1 equals 0? Why is it not 7x squared minus 1? Why don't we use the number on the numerator, the thing on the numerator rather than the denominator?
We have to do both. So to find critical numbers, got to look for where the derivative is undefined, and you also have to look for the derivative equals 0.
Yeah.
So Basically,
part-
we found that there are no critical numbers where the derivative is undefined.
Yeah.
So that's what I'm saying here. So our search for critical points that way didn't find anything.
All right.
But yeah, you're right. We also need to do this.
Okay.
And this is going to give us values. So I get x equals plus or minus 1 over the square root of 7. So do I have two critical points then?
Yeah, in that case, yeah, you do. That helped.
So actually, I just have the one.
Oh well, yeah.
Why do I only have one?
Because it's the bound.
Yeah. So yeah, only the positive one matters. The other one's not going to be on. Or yeah, that
Right.
shouldn't have. So I found my only critical point. So if I want to find the absolute extrema,
You gotta plug that number in.
okay. So basically,
To the
I have to
normal
look here. So f of 1 over radical 7.
Right.
That's going to be equal to negative 1 over radical 7 over 2. What else do I need to look at?
I guess you need to look at the values of the functions for 0 and 2.
Right. Also need to look at the ends because so absolute extrema can happen. They can either happen anywhere where the local extrema might happen. So that's why we looked for the critical points.
Right.
They also might happen at the ends. So f of 0 is 0.
Right.
And then f of 2 is negative 2 over 29. So I think I have clearly found my maximum.
Right.
And then it's just a matter of figuring out which one of these other two things is smaller.
Yeah.
Which I can't I can't see for certain.
No, it's all right. I got it.
Okay.
Question, while he's doing that, for f of 1 over radical 7,
Yep.
you plugged that into the original equation, right?
Yep.
Okay, and you got, okay.
You want to see how I got that?
Yeah.
Okay, sure. So negative 1 over radical 7. Try that again. All over 7 times 1 over radical 7 squared plus 1 equals negative 1 over radical 7 over 7 times 1/7 plus 1. Anything else on this one? All right, Gabriella, what do you have?
Nothing in particular, but I guess like 2.7 with the word problems.
Okay. You don't have a specific one though?
No.
Okay.
I actually had one of those questions in mind.
Yeah, let's do that one then. Is that okay, Gabriella? Or did you have like a specific question?
No, that's just like what I needed help on the most.
Okay. Yeah, Jonathan, go ahead.
Okay, I'm doing number 11. It says if a snowball melts so that its surface area decreases at a rate of 1 centimeter squared per minute, find the rate at which the diameter decreases when the diameter is 10 centimeters.
Okay, so snowball melts at rate of what?
1 centimeter squared per minute.
Okay. And then, yeah.
Find the diameter. At which the diameter decreases when the diameter is 10 centimeters.
Find rate at which diameter decreases when diameter is 10 centimeters. Okay. All right. So how should we start this thing?
I like to draw a picture first. So
Okay.
it would be a sphere. And I like to do the radius in the middle and stuff like that.
So yeah, I think that's a good move here is to let's stop thinking about the diameter of this thing and do radius instead. All right, so we have a sphere, not a circle. All right, so we got a picture. What else do we need to take a bit or need to pay attention to?
That it says when the diameter is 10 centimeters, but for us, it would be the radius, which is
Okay.
5.
So let's substitute this when the radius is 5 centimeters. Okay. So what information is important?
The rate at which it's melting.
The rate at which it's melting. So what can I call that?
Can you use, can you call it just a random variable or?
I mean, it's not random. And I think that's what I'm kind of hinting at. We should probably figure out what all the variables are that we need to think about.
Gotcha. Okay.
So definitely T is the time elapsed in seconds. What else?
The radius, right?
Yeah, so Ray is the radius of snowball. That's in centimeters. What else?
Is there anything else?
Yeah, there is. There's one more thing we need.
It's the rate that you're given.
Yeah, so the rate I'm given, what is that a rate of?
It's the rates of melting.
Right, but so what? Yeah, it's how fast the snowball is melting, but what's it a measurement of? Like what unit is it?
Minutes. It's in minutes.
Well, I mean, time is. Oh, that's not what I was getting at, but yeah.
Okay.
So yeah, what measurements of the snowball is that rate given in? So yeah, it's something. It's something
Yes.
per time.
It's centimeters cubed.
Is it cubed or squared?
Centimeters squared over minutes.
So if it's centimeters squared, what's that a measurement of?
Surface area.
Yeah, surface area. I'll call it capital A. So surface area of snowball. That's in centimeters squared. So, and then the associated rates I'm going to have dA dt. I'm going to have dr dt. And that should be it, right? All right, so I got my variables. I got a crude diagram, but maybe that's all I need of the situation. So what can I do from there?
I'd want to fill out the rate of which we're given.
Okay. So which rate are we given, dAdt or drdt?
DRDT.
No, we're actually
Right.
given dAdt.
Oh, okay, my bad.
So
yeah,
drdt is the one I want. And then dAdt, I think, is -1 centimeter squared per minute. So now how do we unite all these things?
We write an equation.
What's that equation going to look like?
Surface area of a sphere.
Okay. What is the surface area of a sphere?
4 pi r squared. That's the original equation. A equals
Yeah.
4 pi r squared.
Oh, did they give that to you?
No.
Oh, okay. All right. So I have this equation. What do I need to do with it?
You need to substitute. Take the derivatives of a and r, right?
Yeah, with respect to what?
Dt.
So I get dAdt equals what? What's the right-hand side going to look like?
8 pi r dr dt.
Here we go.
And then
Right.
you can substitute the -1 for dA over dt, right?
Yep, I know that one. Equals 8 times pi. Do I know r?
5. Oh, yeah.
Yep. Do I know drdt? Nope, that's the thing I want. So from here, I get -1 over 40 pi equals drdt. But if you're looking at the answer to this question, that's probably not exactly what we have, right? Because, so I think they wanted the rate at which the diameter decreases, right?
Find the rate at which the diameter decreases when it is 10 centimeters.
Okay. So if the radius is decreasing at this rate, what does that mean about the rate of change of the diameter?
Would you just multiply by 2?
Yeah, it's just going to be double. So the answer you have is probably 1 over 20 pi.
Gotcha. Cool.
But yeah, so just this is probably one of the more difficult things we've done this since the last test. But yeah, just going from how do you go from the description of the problem to organizing all the data you have to the equation and then finally the solution. Gabriella, you have a question?
Why did we multiply it by 2? Or
So early on, so this right here is dealing with radius, but what they asked for was something dealing in diameter.
Yeah. Okay.
So, and really what you could have done here is, I know that this is the equation for the surface area of a sphere. But let's say I didn't want to, let's say that you really wanted to keep this thing in terms of diameter the entire time. What you could have done is this. I know that the radius is just the diameter divided by 2, right? Actually, this is going to make everything look so much nicer, isn't it? So the area of surface area of a sphere is just pi d squared. That would have come out pretty nice.
So on the test, if we have something like this on 2.7, are we just, and if it deals with surface area or volume, are we just gonna have to know volume and surface area off the top of our head, formulas.
I mean, yeah, I mean, I'm not going to give you any like, not on a test anyway. I'm not going to give you like any out of the ordinary shape.
Okay, cool.
But yeah, like, spheres, circles, squares, cubes. What else have we done? Cylinders, cones. Yeah, I'm not going to give you anything outside of the basic ones.
Okay, cool.
All right. Sebastian, back to you.
Sorry, I was muted. Okay. Let's see. Yeah, so basically number 3 on 3.7, the question was the limit as x approaches to pi over 2 on the right side. And then cosine x over 1 minus sine x.
Okay.
Yeah, that's right.
All right. So how do we start?
So obviously we know we could use the Hopital's rule because it goes to 0 over 0. It's differentiable, or whatever the word is. And then from there you want to get the derivative of that whole thing.
Okay, so this will be negative sine x over negative cosine x.
Yeah. And then it becomes positive. And then you could plug in pi over 2, right?
Yeah, you're going to get what? 1 over 0?
Yeah.
Yeah.
So that seems like it's the same issue that I ran across last time.
No, no, this is different.
Oh, is it? Okay.
Yeah. So now I got 1 over 0. So what can I do with that?
I'm not entirely sure because that doesn't work correctly.
So that, not a number, right?
Yeah.
So something I would ask you to think about is this: what's the limit as x approaches pi over 2 from the right of tangent of x? Because that's the same thing, right?
Yeah. Well,
So think about what the tangent function does as x gets closer and closer to pi over 2.
It just like it goes to infinity, right? When it's like graphed.
Infinity or negative infinity?
Wait, from pi over 2 from the right.
Mm-hmm.
I guess negative infinity.
Yeah, it should go to negative infinity. So let's look at the unit circle here.
Mm-hmm.
So we are looking at pi over 2, right?
Yeah.
But we are looking at it like as you're coming from above. So because of that, if I look at the unit circle over here, so basically what's going to happen is this: I'm going to be, as I get these angles that are bigger than pi over 2, but approach pi over 2, then you're going to have like points on the circle like this, right?
Yeah.
So as you have these points, think about, what's their sign value going to be? Is it going to be positive or negative?
Positive still.
And what's the cosine going to be?
Negative.
So you're going to have a sign value that's getting closer and closer to positive 1, and you have a cosine value that's getting closer and closer to 0.
Yeah.
But they're getting closer and closer to 0 from below, from the negative. So because of that, your limit's going to be not positive infinity, but negative infinity.
Okay. I guess I could also graph that so I could visualize it better.
Yeah, so I mean, you can graph it, and so if this is pi over 2, and this is negative pi over 2, so these are going to be asymptotes, right?
Yeah.
So in between these two things,
Oh, I see. It definitely is going to.
and then really this behavior just repeats.
Hmm.
So because of that, really you're looking at this behavior right here.
Got it. Okay, makes sense. Thank you.
Yeah, no problem. All right. Jonathan, got anything?
I give you the question that I had coming up. You can go to the next person. I'll probably have one by then, but I'm just
Okay.
looking for those.
All right, Hugh.
All right, I had a question about L'Hopital's.
Cool.
The question was the limit as x approaches infinity of the quantity 1 plus 8 over x to the power of x over 6.
Okay. All right. So where do we start? Hey, Lizzie.
I'd say, well, test infinity. I mean, we already know that it's going to end up being infinity over infinity from doing that.
Get out. 1 second. Okay. All right. So, yeah, we have an indeterminate form, right? But what kind?
Infinity over infinity.
It's actually not infinity over infinity.
Oh. Would it be? Well, I believe it's actually since it would be. Well, it's infinity.
So the
I
inside,
actually don't remember.
the inside of the parentheses, what's that going to go to?
I'm not sure.
Okay. So as x gets really, really large, 8 over x is going to go towards 0. So the inside of that parenthesis is going to go towards 1. But this exponent, this x over 6, as x gets really, really large, that's going to go towards infinity, right?
Yeah, that one goes toward infinity.
Okay. So you have.
Is that one of our indeterminate forms?
All right. I'm sorry. Go ahead.
Is 1 to the power of infinity one of our indeterminate forms?
It is, but it's not one that L'Hopital rule can handle directly.
Okay.
So we got to do some manipulation here to help. So one thing I'm going to do is give this a name. So I'll say y is equal to the limit as x approaches infinity of 1 plus 8 over x to the x over 6.
Okay. And then I think you'd take the natural log of both sides.
Yeah. So I mean, and the thing here is the thing that makes this really hard to deal with is the fact that we have, so our limit is all about x. We want x to approach something, and that variable is in our exponent. So yeah, we can take advantage of a log to make that work for us. All right, and the whole reason to do that is this. Okay. Now from here, was the exponent x over 6 or 6 over x?
X over 6.
Okay. All right. So from here, what can I do?
Well, you can, I guess, just take the derivative of, well, I guess you could separate them still, but.
How about I just separate them into what?
Or well, actually, never mind. That's not right.
Okay.
You could take the derivative of, well, I guess x over 6. Can you separately take the derivative of x over 6 and 1 plus 8 over x?
No,
Or like the
because so
natural
this is
log of- because
so
I
this
feel
is
like you
still an
can't-
indeterminate form. This is 0 times infinity,
Mhm.
but that is not. I mean, the L'Hopital's rule is only useful for things that look a certain way. I mean,
Okay.
it's only good for this 0 over 0 form or this infinity over infinity form.
Ah,
So if we can get to a place where our expression looks like that, then we can use L'Hopital's rule.
all right.
So,
I'm still not 100% sure where to go from there, honestly.
so we have 0 times infinity, right?
Uh-huh.
So we can take advantage of that because, I can rewrite my expression. So instead of it going to 0 times infinity, it can go to something that looks like, infinity over infinity. And the way I'll do that is like this: natural log of 1 plus 8 over x over 6 over x. Basically, I just brought that 6
Yeah.
over x.
Okay, that I wasn't sure if you could do that or not. I didn't
Oh yeah,
know.
absolutely. So, instead of multiplying by the fraction x over 6, I can divide by its reciprocal.
Right.
So now in this case, I have natural log of 1. Like this, now I have this in form 0 over 0.
Right.
Which means now you can use L'Hopital's rule the way it's designed.
Okay.
So then natural log of y is going to be equal to the limit as x approaches infinity of, what's the derivative of natural log of 1 plus 8 over x?
Well, I think it's going to be like 1 over 1 plus 8 over x times, I guess it would just be the derivative. So 1 over x or 1 over, well, I guess just 1 then in that case, right?
No, it's going to be the derivative of 1 plus 8 over x.
Oh,
So that'll be negative 8
right.
over x squared.
Yeah.
So that's one derivative. Now I need the derivative of 6 over x. And that'll be negative 6 over x squared.
Okay.
So the good thing here is that I can just look at these by themselves and realize that a lot of things cancel.
Mm-hmm.
So now what I have is this: the natural log of y equals the limit as x approaches infinity of 8 over 1 plus 8 over x.
All right. And I mean, I believe that would work.
Yeah, that can be done. Oh wait, I've lost the 6. I'll just call this 8 over 6 over 1 over 8 plus x. Or sorry, 1 plus 8 over x. So now if you take that limit, what do you get?
Well, we didn't take the natural log back on the other side. So I know the final answer is going to be a bit different, but.
What do you mean we didn't take the natural log back?
Well, the natural log of y still remains.
Yeah. So yeah, we still have to do that, but right now we can evaluate this limit.
Yeah. So I think it should just be 8 over 6 over 1.
Yep. So natural log of y equals 4/3.
Right.
Which means what does y equal?
Well, I guess just e to the 4/3.
Yep.
Okay.
How did you guys get 4 over 3?
How? Is that what you asked?
Uh-huh.
So it is on the bottom of my page here. That denominator is 1 plus 8 over x. As x gets closer, as x gets larger and larger, that's going to trend toward 1 plus 0. So that whole limit just becomes 8 over 6 or 4/3.
Yeah, it makes sense now.
All right. Anything else, you?
No, that's it for me.
Gabriella, you're back up.
Can we do 2.8 from the homework? Problem 5.
Sorry, which one from the homework?
Problem 5, 2.8.
2.8?
Yeah.
Yeah, what is that problem?
It says the edge of a cube was found to be 30 centimeters with a possible error in measurement of 1 centimeters.
So 30 centimeters
Mhm.
with possible error.
Of 0.1 centimeters. And then use differentials to estimate the percentage error to the nearest 100.
Estimate percentage error of what?
Nearest 100 in computing the volume of the cube and the surface area of the cube.
So percentage error is volume and surface area, right?
Mhm. Yeah.
Okay. All right, so let's do volume first. So how do we handle this?
Don't we need the volume of the cube?
What's the volume of the cube?
Wouldn't it just be like x to the third?
Yeah, so yeah. Whatever the edge is, called x.
Yeah.
All right, so now I have that equation for volume. Now what do I do with it?
Oh, do you use the 30 centimeters for the x?
Yeah, we can find the volume. So the volume is equal to 30 centimeters cubed, and that gives us 27,000 centimeters cubed.
Mhm.
Okay, so that's one thing I'm going to need.
Yeah.
All right. So what else do I have to do to figure out what this possible or what the percentage error might be?
Would you have to like multiply by the 0.1%?
Multiply what by 0.1?
The 30 centimeters, the volume?
Not the volume, but really what we're looking at here is, this error is going to be a rate of change. So
Okay.
because of that, I need to take a derivative.
Okay.
So if I take a derivative of the volume with respect to x, I got dv dx equals 3x squared.
Mhm.
And then where the differentials come in is I'm going to multiply both sides by dx. I got dv equals 3x squared dx. So from here, I'm looking for what the dv is going to be my change in volume. That change in volume, that's what my possible error is going to be represented by.
Okay.
So my possible, not percentage error, just error, it's going to be equal to 3 times whatever I believe the side length is, times the possible error, which is 0.1 centimeters. So that comes out to, I believe, 270 centimeters cubed. So my possible error is 270 centimeters cubed. So the way I find the percent error is by taking my my pure error and divide it by the volume, the nominal volume. You know, the volume that I would have if all my measurements and calculations were perfect. And then multiply that by 100%. And I get 270 centimeters cubed over 27,000 centimeters cubed times 100%. And I think that comes out to be 1%.
I have a question in regards to this.
Yep.
I forget what it's called, but I remember when we did these questions like in our notes and in the homework, there would be something where we would take the volume plus or minus whatever value we got for dV. What would that be? What was that called?
I mean, we just didn't write it in that form, but you know, I could say that my volume in this case is 27,000 centimeters cubed plus or minus 270 centimeters cubed.
Okay. And what does that like display?
What's that?
What does that show us?
Basically, I mean, that's kind of like an interval for what my volume could be. Because I mean, you know, if all my measurements and calculations were perfect, the volume would be 27,000 centimeters cubed. But I could be wrong by 270 cubic centimeters, you know, either high or low. So I'm not sure if any of you have ever taken like an electrical engineering lab, but if you work with resistors, you know, a resistor might have a value of like, it might say, okay, this resistor is 1,000 ohms, but when you measurement, it's almost never exactly 1,000 ohms because it has, you know, they're manufactured with some kind of error in them, which is okay, but same kind of thing here. All right, Gabriella, you also want to do the surface area, so how would we handle that?
The original, would it be 6x squared?
Yep, so that is the equation for surface area of a cube.
Mm-hmm.
Now what?
And then we'd find the surface area with the 30 centimeters.
Yep, so we'll find the nominal.
Mm-hmm.
So that comes out to 900 times 6. So 5,400 centimeters squared. All right, now what?
Do we find the derivative?
Yep.
Of the 6x squared?
So we'll go dA dx
Mm-hmm.
is equal to 12x. So dA is equal to 12x dx. This is where our error will come from. So 12 times 30 centimeters times 0.1 centimeters, which is equal to 36 centimeters squared. So our error this time is just 36 centimeters squared. All right. So from there, how would I find the percent error?
Wouldn't you multiply it by 0.01?
Oh, I did that. That's what this bottom line here is.
Oh.
So my possible error is 36 centimeters squared, right?
Mm-hmm.
So now how do I find the percent error that goes with it?
I'm not too sure.
Okay, so I found basically I'm going to do something similar that I did with the volume. I found what the possible error in surface area was, which is 36 centimeters squared, and now I want to take that as a ratio of my nominal area. So it'll be 36 centimeters squared over 5,400 centimeters squared times 100%.
Mhm.
Which I think is 0.667%. All right. Anything else on that one, Gabriella?
No, thank you.
Okay. All right, Sebastian.
Yeah, let's see what else I had. I'm pretty sure this one is similar to what we just solved together, but I think I will still go over it.
Okay.
It's the limit as x approaches 0 from the right. Ln x over x.
Okay.
And so we know that ln x. I'm pretty sure that goes to infinity over infinity, right? Or I could be wrong. Or yeah.
I think it's going to go to. So
Okay.
natural log of, as x gets closer and closer to 0, I believe natural log of x is going to go closer and closer to negative infinity. Like it's going to get just
Yeah,
going
it
to keep
does.
decreasing.
Mm-hmm.
But what's the denominator? What's the denominator going to do?
That's going to go to positive infinity.
No, you said x goes to 0, right?
Oh, did I? Yeah, it does.
Yeah. So this is not indeterminate.
So, like, if I have y equals x graphed, it's obviously just like that.
Yeah, it's a straight line, right?
Yeah, it's a straight line. So like approaching 0 from the right. How is that? Is it because it just goes to 0? Is that why?
Yeah, I mean, so yeah, y equals x is continuous at 0. So yeah, you can just plug in 0.
Okay, so it's not indeterminate, and so what does that mean for us?
So you don't have an indeterminate form, which means you are not allowed to use L'Hopital's rule. So we got to find the limit some other way.
Okay.
And I think let's just kind of think about what this does. So as x gets closer and closer to 0, your numerator is getting really, really small with no limit. So you could give me any negative number you want, and I could find a value of x whose natural log is equal to it.
Yeah.
And then you have your denominator, which is getting closer and closer to 0. So basically what you have is you're dividing numbers that are getting very, very small with no limit, and you're dividing those by numbers that are getting, also numbers that are getting smaller and smaller, but they have a limit of 0.
Okay.
So what is that overall result going to be?
Can you say that again one more time? So
So you're dividing numbers that have no limit. They're just getting smaller and smaller and smaller.
Yeah.
And you're dividing them by numbers that are getting closer and closer to 0, but they're staying positive.
Okay.
So think about what's going to happen there.
Would that just be going to negative infinity?
Yeah. So basically, and let's do a table to drive this home a little more. So if I go 1, 0.1, 0.01, 0.001, natural log of 1 is 0, x is 1, so that'll be 0. Natural log of 0.1 over 0.1 is negative 23. Negative 460. And then negative 6,008.
Okay.
6,908. So, yeah, I mean, as x gets closer and closer to 0, you know, the right-hand column here is just you're gonna get these numbers that keep getting smaller with no bound.
Okay. And we're allowed to have our calculators on the test, right? In
Yep.
case we want to okay.
Yep.
Got it. Yeah, that's basically it for me. I just was hoping to go over some other review questions as well for other people.
Okay, cool. All right, Jonathan, you're up.
Okay, I'm looking at inverse functions.
Okay.
It says for find the derivative of the function and simplify where possible. And the one I was looking at is y equals arc cosine, and within that it's arc sine t. And then
Okay.
on top of that, I couldn't find. I was wondering. This isn't really a question, but the ones where we would look on the unit circle, you give us cosine pi over 2 or something like that.
Yep.
Are those located here as well? Because I don't see them.
Yeah, it was in the same section where we did
Okay, here it is. Yeah, it's in 1 through 6. Okay, yeah.
Yeah. Okay, so we're trying to find a derivative of this?
Yeah.
Okay. All right, so how can we handle this? Or I guess dy dt.
Well, you take the derivative of arc sine t first, right?
Depends. What do you want to do? What else are we going to have to do?
So you have to take the derivative. We have to do 2 steps that I knew of right now. So arc sine t, you're gonna have to take the derivative of that, and then you're gonna have to take the derivative of arc cosine, and then whatever's inside that.
Okay. So what's the derivative of arc sine of t?
Is just arc cosine?
No.
No.
It's 1 over the square root of 1 minus t squared.
Oh, okay.
And then the derivative of arc cosine t is negative. That's the same thing. Negative radical 1 minus t squared.
Okay.
So based on those 2 facts, how can I handle this overall derivative?
So couldn't you do this the method that I was talking about, where you take the derivative of arc sine and then t, and then take that derivative, and then sorry, I'm kind of confused. And then take the derivative of arc cosine, and then take the derivative of the. I don't know. I'm confusing myself. Sorry.
Okay, so look at the way arc cosine and arc sine are related here. Does that tell you anything about the approach we're going to have to use with this derivative?
Can you just use the chain rule?
Yeah, you got to use the chain rule.
Yeah.
So how do you want to set that up?
So arc cosine would be 1, and then arc sine t would be another.
Yep, so we got both of those.
And then you just take the derivatives, right?
Yep, so got to handle the outside layer or the outside function first. So what's the derivative of arc cosine?
That's negative 1 over square root 1 minus t squared.
Right, but are we going to reuse t, or are we going to use something else there?
Oh, okay. And then that instead that would be arc sine t, right?
Yeah, 1 minus arc sine square root of t. So that's the outer layer for the chain rule. Then I'm going to multiply this by what?
And you multiply it by 1 over square root 1 minus arc cosine squared to the t.
Nope, just t squared.
Okay.
Because so in chain rule, you got to go from the outside in, right? So the derivative of arc cosine is -1 over radical 1 minus t squared.
Gotcha.
But when you're doing chain rule, you have to respect like what is the outer function evaluated at? What is the input to that outer function? And the output to arc cosine is arc sine of t.
Okay.
So that's why in this first term on the left here, you have -1 over radical 1 minus arc sine squared t.
Okay.
Then we got to go inward with the chain rule. So from there, our inner function is arc sine of t. And it's just arc sine of t. There's like nothing, it's not like t squared or anything more complicated than that. So the derivative is just 1 over radical 1 minus t squared.
Okay.
Can you say the last part again, actually?
From where? Sorry.
So
let me set this up the way that we usually do. I'll call this y equals f of g of x. So f of x is going to be equal to arc cosine of t. G of x is going to be equal to arc sine of t. I guess I should be calling all these t's. So think about what happens to t. It goes to the first function g, and that transforms it into arc sine t. Then that goes through the function f, and that transforms it to arc cosine of arc sine t, right? So then when I differentiate, I have to differentiate from the outside in. So I'm going to take the derivative of f, but what is the input to the function f? The input to the function f is g of t. So that's handling the outermost layer. Then I have to differentiate the function g. And since g is the innermost function, the input to it is just t. So this is going to be my chain rule. This is kind of my template for it. F prime of g of t times g prime of t. And I already wrote down what f prime of t is. That's -1 over the square root of 1 minus something squared, right? But in this case, that something is whatever the output of g is. So in this case, that's arc sine t. So this right here is f prime of g of t. The rest of this is going to come from g prime of t, which I already wrote down, is 1 over radical 1 minus t squared. And that part right there is g prime of t.
got it. Makes sense now.
Yep, good. All right, Hugh, you're back up.
I don't think I have any more questions. I was kind of just sticking around to see if anyone said anything like interesting that I wanted to see.
Gotcha. All right, Sebastian, back to you then.
I don't really have anything in particular, but I could see if I have any homework questions. Like I typically take photos of the questions I need help with, but give me a
Okay.
minute.
Okay.
Could I ask a quick question?
Yeah.
Okay, so I'm looking at the 3.5 exercises, and it says find the exact value of each expression. So there's two parts to them. I think the most complicated ones are probably tan, and then inside that is arctan 10.
Okay.
And then part B is arcsine, and that is sine 7 pi divided by 3.
Okay. All right, so the first one, the tangent of the arctangent of 10. So how can we handle that? Or how can we start? I mean, really, it's tough to think about all at once, so how can we start that?
Do you want to look at tan as sine over cosine instead?
I don't think that would make it any easier. I mean, it's definitely true,
Okay.
but I don't think that would make it any easier.
I'm sorry, are we just trying to find the derivatives of these, or like what are we looking for?
No, we're not looking for derivatives. We're looking for basically just evaluate that expression.
Oh, okay.
Why would you think that's what?
I don't. The arctans. The only problems I have is with the tangents and the arctangents. So I don't know where to go from here.
Okay, so what was it? Tangent of arctangent of 10?
Yeah.
And what was B again?
And then B was arcsine sine 7 pi over 3.
Arcsine sine?
Yeah. 7 pi over 3.
Okay. All right. So I mean, you said the tangent are the only ones you're having problems with?
Yeah.
Okay, let's handle the arcsine one then, because really they don't behave all that differently. So,
okay, so first I would normally make a unit circle, but that takes too long. Let's see if I have mine on hand right now. Give me a sec. So I would look for that's a value with inside the circle. So 7 pi over 3 is closer to the 1 mark. So that's in the fourth quadrant. Is it?
I don't think it is in the fourth quadrant.
Isn't it? I swear it was.
I think it's in the first.
One second. Wait, let me look real fast. It's 7 pi over 3.
Mm-hmm.
No, there's. Wait, one sec. There's a 7 pi over 4. But,
So here's the problem. 7 pi over 3 is the same as 6 pi over 3 plus pi over 3, right?
okay, yeah.
So it's an angle that's bigger than 2 pi, which I think is why you're not seeing it on your whatever you're looking at.
Oh, okay, gotcha.
So because of that, I know I'm really looking at the angle.
Gotcha. Okay.
So I mean, if I want to represent it, I'm going to go a full rotation.
So then in that case, you get half for that, or no. Radical 3 over 2.
Right. So yeah, sine of 7 pi over 3 is the same as the sine of pi over 3, which is radical 3 over 2.
Over 2.
So now what you want is the arcsine of radical 3 over 2.
And then can't you also just say sine x equals radical 3 over 2? That's
Sine of x equals radical 3 over 2. Yep.
And then that would be, would that be 2 pi over 3?
Nope. I mean, let's think about it this way. So arcsine is a function that has a very specific domain, right? What's the domain of the arcsine function?
Pi, isn't it pi over 2 or negative? Is it negative pi over 2 to pi over 2 or pi over 2 to negative pi over 2?
I mean, those are the endpoints of the interval, right? Usually you give the least, the lower one first. So yeah, negative pi over 2 to pi over 2, right?
Right.
So 2 pi over 3 could not be a value for this x because it's not even inside that
So
even inside that range.
So then would it just be pi over 3?
It's pi over 3, yeah.
Okay.
I mean, I think that's why drawing this diagram was helpful, because you see you're in the first quadrant. I know this reference angle in the first quadrant is just pi over 3.
Right, okay. Gotcha.
All right, so over here, arctangent of 10. I'm going to suspect that one thing that's tripping you up is that the fact that, you know, this is not an angle we understand. Like, this is not like one of the special angles on the unit circle that you can know exactly. So all we really know is that there's some angle, we'll call it x, where tangent of x equals 10.
Mm-hmm.
Now, think about what the range of the arctangent function is. What's the range of that function?
I don't have this one memorized off the top of my head.
Okay. This one's negative pi over 2 to pi over 2.
Okay.
Not
Same
included.
thing?
No, well, not quite, because it doesn't include the endpoints. Like with arcsine, you know, I can have the arcsine of 1, and that's equal to pi over 2. So the range of the arcsine function is from negative pi over 2 to pi over 2, including the endpoints. Arctangent, the range does not include negative pi over 2 or pi over 2.
Okay, so it's instead of closed brackets, it's open brackets.
Yeah. So what we really know is, so I'm only looking at the first quadrant and the fourth quadrant. So I have an angle x whose tangent value is 10. Is that going to take place in quadrant 1 or quadrant 4?
Quadrant 1, right?
Quadrant 1, how come?
Well, because it's an even number.
Not that it's even. I mean, it doesn't even have to be an integer, right? It could be like the arctangent of like 1/2.
Right. Okay, but I don't see why does it why, so if my answer is wrong, because it's even, then what would the other answer be?
So think about what happens when you take the tangent of an angle. It's equal to sine of x over cosine of x, right?
Right.
Where is the sine of an angle positive? What quadrants?
Quadrants 1 and 2, right?
Right. And where's cosine positive?
1 and 4.
Yeah, so positive in 1 and 2. This is positive in 1 and 4. So the only way for tangent to be positive is if sine and cosine are both positive or both negative, right?
Right. So because the 10's positive though.
Yes. Yeah, not even, because positive.
Oh, sorry. Yeah, I meant positive.
Oh, you did mean positive? Okay.
Yeah. I don't know why I said even.
Okay. So I can say that x definitely lives in this quadrant. I'll just say opposite side 10, adjacent side 1. So you have some angle x whose tangent is 10, right?
Mm-hmm.
So then basically I can boil this statement down to this. What is the tangent of x? What is the tangent of x?
That would be some like 1.5.
No. How'd you get 1.5?
I don't know.
How did you get, so what does it mean? What does tangent of x mean?
Just sine over cosine.
Sine over cosine. Is that something I already know about this angle x? Remember, x is not really a variable the way we're talking about it. Like it is, x is some angle that we already know a lot of stuff about.
I don't know.
So the tangent of x is 10.
10? Okay.
So think about it this way. If we start from the inside out, we have arctangent of 10. That means I want to find an angle. And I think we even call it x, right?
Right.
I want to find an angle x that has a tangent value of 10. So that's where I drew this picture over here, right?
Mm-hmm.
And basically what the rest of this, if I go outward from there, what I'm really asking is, all right, I found this angle x. So what's the tangent of it? Well, remember that the way we built this angle x was that is that the tangent of x was equal to 10.
Right.
So basically what this thing is asking, this whole statement is, what is the tangent of the angle that has a tangent of 10?
Okay.
Does that make sense, or should I try again?
No, I'm following.
Okay. So basically, I mean, you can think of, maybe it'll be even more clear if I write like this: tangent of inverse tangent of 10. Because really, tangent and inverse tangent, they are inverse functions of each other. And the only reason that this one right here, arcsine of sine of 7 pi over 3, what's the reason that that is not equal to 7 pi over 3? Like, how come we couldn't just cancel out there?
Okay. Because you're taking the sine first and not the arc sine, right?
Right. So because you're taking the sine first, think about what the range of arcsine is. The range of arcsine does not include 7 pi over 3.
Right. Okay.
So that's why I can't give you that value back.
Gotcha. So then at the end, would this just be 10?
Yep, the answer's 10.
Okay. Okay.
I mean, something that might make you feel better, like actually go to your calculator and figure out what the inverse tangent of 10 is. I think you said 1.5, which is probably close to what this is.
It's 1.47.
1.47?
Yeah.
And then if you take the tangent of 1.47, you better get 10.
Yeah.
Yeah. So, I mean,
you get like
basically
9.9 something, but
yeah, just what is within the rounding of your calculator. But yeah, basically you're just, that tangent of arctangent of 10, you're just asking for, you're kind of asking for the same information in opposite ways.
okay. But if it's
like if I said, what's the square root of 5 squared?
That'd just be 5.
Yeah, so it's the same kind of idea there. Like in the question, I gave you the inverse of an operation, so they kind of annihilate each other.
Gotcha. But the only time that doesn't, so if it was arctan tan 10, you'd have to do more stuff to it though.
Yeah, I mean, so let's think about that. I need, let me get another page. Because it's really all about what language you're speaking. So if you had arctangent of tangent of 10, in the last question, the number 10 represented some ratio, right?
Right.
It was just like, yeah. So yeah, some ratio, some like length. In this case, what does this 10 represent?
That's your angle, right?
10's an angle, right? So that's like 10 radians. You know, which is a lot more than 2 pi.
Right. Okay.
So because of that, yeah, taking the arctangent of whatever this comes out to be is not going to give you 10 back.
So if I see anything like the previous one on the quiz, or the test, it's just basically the thing inside that arctan.
I mean, it all comes down to, you know, think about this input here. Like, think about how that is. Think about what that represents. Like, for example, if you were talking to someone from another country and you were talking about how much something costs, you better be talking about more than numbers.
Right.
Because there's a possibility that one of you is talking about one currency and the other is talking about something else. And the same kind of thing with trig. I mean, okay, does 10 represent a measurement of an angle, or does 10 represent, you know, some ratio that has to do with some other angle?
Right. Okay.
So I think the bottom line that I would point you to is that it's all a matter of, you know, if you're working from the inside out, what kind of a function are you looking at? And because of whatever kind of function that is, what kind of object is the input? Is it an angle or is it some other measurement?
Okay. Well, thank you.
Yeah, of course. All right, Hugh, anything?
Yeah, I just wanted to make sure so the bounds of inverse functions for the inverse, I guess sine and inverse tangent functions, they're bounded to -pi/2 to pi/2, right? Or I guess quadrants 4 and 1.
Yes, but there's one important difference. So what is the range of the inverse sine function?
Of the inverse sine function, isn't it?
Yeah.
Oh, I see what you're saying. So it's the range of the inverse sine function is just, well, isn't it -1 to 1? Like, doesn't
No, that's the
depend on
domain.
period? Oh, okay. So it's -infinity to infinity
No.
for the range.
So I mean, you already said that. I mean, so let's talk about this in terms of sine as well, right?
Mm-hmm.
So I think the range of the sine function is a little easier to see. So the range of the sine function, like if you were to, for example, if you were to graph out a sine wave, what's the highest and lowest it could be?
1 and -1.
Right. So because of that, since the range of the sine function is -1 to 1, the domain of the inverse sine function is -1 to 1.
Yeah, but not the range.
Not the range. So yeah, what's the range of the inverse sine function?
Is it not -infinity to infinity?
It's not, because yeah, if you took, like, for example, if you went to your calculator with the inverse sine of like 20, you get an error.
Okay.
So remember, just to jog you, remember what we did with the sine wave here is, you know, if you graph the sine wave like this, so if this is the sine wave, the sine function, the graph of it, I can't invert this thing because it's not 1 to 1, right?
Yeah.
So I had to cut this thing down a lot to make it 1 to 1.
Oh.
Remember that?
Oh, yeah, I do remember that.
So what angles did I have to limit it to?
Well, I guess -pi/2 to pi/2.
-pi/2 to pi/2.
Right.
And because it's the sine function, I can use the values -pi/2 to pi/2. So that's why I include those.
Okay.
But the inverse tangent function, you know, it's got the open interval -pi/2 to pi/2, because think about what tangent of pi/2 is. That's equal to sine of pi/2 over cosine of pi/2, which is equal to 1 divided by 0.
All right.
So at those angles, since the tangent doesn't exist, the inverse tangent can't possibly give you those values.
All right.
I'll say
so-
one more way I can say that might make more sense. Since pi over 2 is not in the domain for tangent, it can't be in the range for inverse tangent.
All right. That makes sense.
Good.
And then I guess for cosine, just 0 to pi.
Yeah.
Okay.
All right, Gabriella, you have anything?
Yeah, I just have a quick question.
Okay.
So for section 2.4, it asked for one of the questions was like, when does the mass pass through the equilibrium position for the first time? What's the equilibrium position? Like, what is that?
Yeah,
mean?
so I mean that's kind of a subtle thing, and I wouldn't worry about that for the test. Homework's a different story, but equilibrium means there's no acceleration.
Okay. Okay.
So I think for that one, you were given like the position. Were you given the position, or were you given the velocity?
The velocity.
So how do you get the acceleration from the velocity function?
The acceleration?
Yeah, the acceleration.
I don't know. Where do we find the derivative? Well, I found the derivative to find the velocity.
Okay, so you can find the derivative of the velocity to get the acceleration.
Oh, yeah.
And then once you have the acceleration, then you can figure out where the acceleration is equal to 0. And those are those whatever times you get from that, those will be the times when the object is at equilibrium.
Okay.
All right, Sebastian, back to you.
Sorry, give me a minute. Yeah, so this is based off the homework. It was question 9. I'm pretty sure I figured it out, but I just want to go over it again. It's the limit as x approaches infinity to 3x e by the power of 1 over x, and then minus 3x. Yeah, 1 over x and then minus 3x. Yeah.
Okay. All right. So what's going on here? How do we handle this?
So the way I would approach this is I would actually, first of all, we would check if we could use L'Hopital's rule.
Okay.
And I'm pretty sure we can. I'd probably check in my graphing calculator, but I'm pretty confident we can.
Okay. So which indeterminate form do you have then?
I would say infinity over infinity.
So, I mean, you're not really even dividing anything. So I don't see how you can get infinity over infinity.
Okay. Oh, yeah, that's true. Well, yeah, sorry. I would have rearranged it. I would have natural logged it, actually.
Okay.
Actually, yeah, let's do that first. So basically, I natural log the whole thing. Sorry, I'm writing this down as well. Yeah, so I got natural log of 3x e by the power of 1 over x over natural log of 3x. Or, yeah, you can write it like that too.
So you can't actually break
and
this
then
down.
rewriting it. You can't break it down. Why not?
No, I mean, so I think you're getting. So this is a thing that's true. But like there is, we're stuck with that. And when you're actually subtracting the arguments to the natural log, can't really do anything with it.
Oh, you can't?
Mm-mm.
Okay. And what did I do here? I'm sorry, I'm trying to look at the work that I did. Yeah, it just seems that actually I didn't even take the natural log. I just actually looked at 3x and I set that to the denominator. So it'd be negative x. So you'd have 3e to the power of 1 over x, all under x, and then minus 3.
Wait a second. So 3e to the negative, 3e to the 1 over x. All what?
Yeah, sorry. So that what you have right there over x, 3e by the power of 1 over x, and then outside of that minus 3. Is that correct? Can you write that?
That is not literally the same thing that we have.
It's not? Okay.
So here's what I suspect you're going for. So to go further, let's factor out an x.
Okay.
So x times 3e to the 1 over x minus 3. So I think it's a good thing that you're trying to get the x out of the denominator somehow.
Mm-hmm.
I just don't think the way you did it works. So
Okay.
let's stick with that goal. Now that I've factored out the x, is there something else I can do to try to get that to the denominator?
Yeah, so you could basically rewrite it. So it'd be 3e by the power of 1 over x minus 3 over x by the power of negative 1.
There you go. Yeah. So now what we have to do is make sure that this is an indeterminate form.
Yeah.
So what happens to the numerator as x goes to infinity?
I'm not entirely sure. I forget. Would it be?
So let's go to a piece at a time.
Yeah.
In the numerator, the only place x appears is in this exponent, right?
Yeah.
So as x gets bigger and bigger, what's going to happen to 1 over x?
It's gonna approach. The 1 over x is gonna be approaching 0. So then
what's e to the 1 over x going to be approaching?
it would just be e to the power of 0, so 1. So then
Okay, so your numerator becomes what?
it basically becomes 3 times 1 times, minus negative 3, so 0.
Right. What's the denominator going to do?
Denominator, that's what I'm not entirely sure about. Would it be going to infinity or no?
So let's think. I really think that, people don't usually think about negative exponents like this, right? So let's rewrite this. What's a more intuitive way I could write that?
Just x.
No, it's not equal to x.
Oh wait, sorry. 1 over x.
Right. And hopefully it's easier to think about what 1 over x does as x gets really big.
Mm-hmm. Makes sense.
Yeah.
Okay. I'm writing this down along as we're going. So from there we just need to get the derivative.
Wait,
right?
So what does 1 over x do as x gets big?
Oh, sorry, it goes to 0.
Okay, so yeah, we do have that form. So yes, we can use L'Hopital's rule now. So what are the derivatives of our numerator and denominator?
It would be 3 over x times e by the power of 1 over x. Right?
I don't think it would be 3 over x.
Because I'm using what is it? Power rule? Yeah, power rule.
No, power rule is not. So power rule is good for when you have, you have e to the 1 over x.
Yeah.
As opposed to, like x to the 1 over 4.
Mm-hmm.
So in the top case here, the e to the 1 over x, the one we actually have, we have a constant base
Oh,
and a variable exponent. So the power rule is really for variable base and constant exponent. So we can't use power rule here, but think about what the derivative of, the simple exponential function. What's the derivative of e to the x?
It would be x e to the power of x.
And it's just e to the x.
Oh, that's right. That's right. Yeah.
So I think what you might be getting tripped on is this. Like, what if it was a little more complicated? What if the exponent here is actually a function of x? Then this derivative will be equal to e to the f of x times the derivative of f. And this right here is just a very specific application of the chain rule. Because instead of e just being raised to simple x, e is raised to another function.
Yeah.
So take the derivative of the outer function, and the derivative of e to the x never changes. So take the derivative of the outer function, then you got to handle the inner function.
Yeah. Okay.
So because of that, your derivative of the numerator is going to contain 3 times e to the 1 over x.
Yeah, it's going to remain the same.
But then I got to multiply it by something.
I'm not sure what has to be multiplied by. It would have to be.
So think about what I did over here in the corner. In this case, your inner function is 1 over x, right?
Yeah.
So basically what I got to do is multiply it by the derivative of 1 over x.
1 over x. Oh, okay, I see. So that's negative x squared, right?
That's squared.
Or oh wait, what is by the power of -2, sorry.
Yeah, it's a -2. So that's the numerator. And the denominator is going to be the thing you just did.
Yeah.
So that's good. Is this a limit I can deal with directly?
Yes.
All right, what's it equal to?
It equals to 3e to the power of 1 over x.
Right, so yeah, that's all that's left is 3e to the 1 over x. But what happens when you let x get really big? Like, we can evaluate this limit now.
Oh, so now if you're gonna plot it, whatever, 1 over x is gonna be approaching 0, so it's gonna be basically e to the power of 0, so which is 1, so it's just 3. 3 times 1.
There you go.
Got it. Makes sense. What's interesting for studying for this exam is that quite literally everything like piles up on top of each other.
Yep.
So just like it's more important, I realized, to like study the latest things because it already incorporates everything we've already covered.
Yeah, I won't say it's always true, but that happens quite a bit.
Yeah.
All right, Jonathan, what do you got?
Give me like 2 minutes. I'm looking for one last problem. So.
Okay. All right, Gabriella, anything in the meantime?
No.
Okay.
Okay, I think I got one.
Okay.
So this is just finding the limits using L'Hopital's rule when appropriate.
Okay.
And it is as the limit x approaches 0, and then it's cosine mx.
MX?
Yeah, it says mx.
Okay.
And then minus cosine nx all over x squared.
Okay. Am I told anything about those M and N?
No.
Okay. All right. So what can I do from here?
Well, you can separate it, right? Or no.
Separate it how?
You can use. No. Could you separate them by just saying natural log? No, that doesn't make sense. Never mind.
No, I wouldn't do that.
Yeah.
One thing, just to maybe you were thinking this, or something I think should be pointed out. In general, if I had something like this, you could break this up like this: cosine of mx over x squared minus cosine of nx over x squared. So these two things are equal, but you can't say the limits are going to be equal if you do that, because I think right now the limits are not going to exist. Because x is going to 0, these are going to, the way this is written right now, these limits aren't going to be defined.
Right.
So just
So we take the derivative.
Can we take the derivative of? So do we have one of those indeterminate forms?
Let's see, cosine mx, cosine 0. Yeah, well, anything zero, it's 0 at the bottom. So yeah, you have to,
Yeah.
right?
So yeah, you do have 0 over 0. So yeah, you can. So what do I do? This is going to be negative m sine mx minus n sine nx
Mhm.
over 2x.
2x. And that's still going to be 0. So
Yep, still going to be 0 over 0. So
take
now
the
what?
derivative again, and then you'd get negative, or wait, yeah, negative, or 2m cosine, or negative 2m,
Not 2m.
or m to the squared.
Yeah, m squared.
M
Negative m squared cosine mx
cosine mx minus n squared cosine nx.
all over
2. Okay. And then that, you can do it from there, right? Yeah.
Yeah, that works. So what's my limit then?
So let's see. Plug it in. So you get cosine 0. Cosine 0 is 1. So then it just be 0.
No, it's not 0. I mean, it's only 0 if m and n are the same thing.
Well,
Remember, what's the cosine of 0?
be 1.
Yeah, so I mean, yeah, so now these are all continuous. So if you plug in 0 to those x's, you get negative m squared cosine of 0 minus n squared cosine of 0.
Okay, so it's just, so then it's that.
Yeah, it's just this weird expression here. Yep.
Okay. Cool. Thank you.
No
I don't
problem.
know if I can find another one in 5 minutes and also do it. So, I mean.
Yeah, I mean, just find one and then let's do it tomorrow.
All right. Sounds good. And this will be posted probably tomorrow in the afternoon, I'm guessing.
This tonight? No, I'll post it tonight.
Oh, okay, cool.
Anything else, anyone?
Can we quickly do the limit as x approaches 0 from the right? 8 sine x natural log x.
Limit as x approaches 0 from the right of what?
Yeah, 8 sine x natural log x.
Okay. Okay.
Okay, let's see. It seems that I just started out by getting the derivative of that, but that's No, that's incorrect. I'm not entirely sure how to approach this. I
Okay,
forgot
so
what I did.
why can we not just take the derivative of this thing as is?
Because we don't know if it complies with the rule.
I mean, so I remember that the L'Hopital's rule only works for these two things, 0 over 0 or infinity over infinity.
Yeah.
I'm not even dividing here.
Yeah.
What I do have an indeterminate form though, and it's as x goes to 0, sine of x goes to 0, but natural log of x goes to negative infinity. That is something that's indeterminate. So what I would like to do is get this to a place where I can, make it friendly for L'Hopital's rule.
Yeah.
So I can try a couple things. I think the one I'm going to try is this. Let's do 8 natural log of x over cosecant of x.
Oh, that's right. Okay.
So now I think I have negative infinity over the cosecant of 0, which is going to go to positive infinity, I'm pretty sure.
Okay.
So I do have an indeterminate form. So now I can take advantage of L'Hopital's rule.
Hmm.
The numerator is going to go to 8 over x. And the derivative of cosecant is, pretty sure it's negative cosecant x cotangent x.
Yes, it is.
Okay. Now, what is going to happen?
We can't just plug in 0 because that wouldn't work.
No, but I'm going to try a rewrite because there's a lot of stuff going on here that I could easily write as, let's do negative 8 sine x tangent x over x.
Okay.
And I think that is still indeterminate because as x goes to 0, sine and tangent both go to 0. So in this case, I have 0 over 0.
Okay.
So I can take a derivative again. It's going to be a little more complicated because I got product rule involved, but it still works. Negative 8 sine of x secant squared x minus 8 cosine of x tangent x all over 1. So clearly I don't have, so now I'm good because I don't have I'm not going to be divided by 0 because I'm not dividing it at all.
Yeah.
So in this case, I should just be able to evaluate. So I have negative 8 times the sine of 0 times the secant squared of 0. Really hope that's defined, and I think it's 1.
Yeah.
Minus 8 times the cosine of 0, which is 1, times the tangent of 0, which is 0.
That's all just 0. Okay. Makes sense.
Cool.
Right.
All right. I think I am going to, I'm going to call it a night, but I'll post this. I'll post this whiteboard and the recording tonight.
Okay.
That's
Thank you.
good. Thank you
I'll see
very
you tomorrow.
much.
No problem.
Yeah. Have a good night.
You too. Thank you.
Thank you. Have a good
Thank
night.
you.